I'm Dr. T, and welcome to my whiteboard. Today I'd like to talk a bit about heating curves. So behind me I have a heating curve. I've got a substance that's starting out at a low temperature, and energy is being added, and it's going up in its temperature, and going through phase changes in the process. By the way, the mirror image where I would be starting high and going down would be called a cooling curve, and literally looks just like a flipped version of this. Absolutely identical. Now, with a heating curve, it's showing me a couple of interesting things, or once again, a cooling curve. The flat spots are phase changes. Where you have a phase change, your temperature doesn't increase, or assuming you have an even heating. Obviously, you can have hot spots, and that's a slightly different story. But assuming the heating is even, or in the case of a cooling curve, the cooling is even, whenever you have a phase change, the energy is going into changing more material into the next phase. Therefore, the temperature of the substance doesn't change. So you will get these nice flat spots. And if your setup for doing this experimentally is done well, you will see these nice flat spots. Kind of as we've talked about previously, the flat spots are going to be governed, at least their length, I should say, will be governed by the heat of whatever phase change you're dealing with. So in this case, presumably, I'm going from a liquid to a gas, so that would be heat of vaporization or heat of fusion. There is an enthalpy for sublimation as well, if you happen to be sublimating instead of doing a melting and then boiling. The lines, on the other hand, are the sloped ones. Those are the warming periods. That's where I'm increasing my temperature, I'm staying the same phase, and that is governed by mcs delta T. A couple quick points though. CS does depend on what phase you're in. Different states of the same thing do have different specific heats. For instance, the specific heat of ice is around 2 joules per gram degree Celsius, whereas water is a little bit over that of 4 for the liquid state. Steam is about 2 in the case of water. Yeah, so we've got this. And we can use this to our advantage in a couple of ways. One, the flat spots are inherently useful. Imagine a double boiler. You're controlling your heat by making sure you're doing a phase change with the water. Okay, let's work some math and get ourselves familiar with how we can use the information from a cooling curve to start calculating total amounts of energy that we're going to need. So in this scenario, I'm taking 27 grams of ice, so solid water, and I'm converting that into 27 grams of steam. And I'll be specific, my ice is at negative 15 degrees Celsius, and the steam is going to be at 112 degrees Celsius. Okay, I'm going to need a fair amount of base information. So I'm going to have solid, liquid, and gas. I need the specific heat for all three. That's there. I'm going to be doing 2 phase changes. I'm going to be doing a melting and a boiling. So I need the heat of fusion and the heat of vaporization. By the way, the asterisks are assuming you're at 1 atmosphere here. Also, I need to know the melting and boiling point for what's going on. Once again, that's this, assuming 1 atmosphere. Okay, what I'm going to do is I'm going to take every segment of my heating curve, and I'm going to solve for the amount of energy that that segment requires. Then I'm simply going to add the whole mess up. Okay, so I'll do my warming of my solid first. Okay, plug in the numbers. That's, once again, mcs delta T. Boom. I'll do the same thing for the liquid, mcs delta T. Notice my CS's are different. And then I'll do the same for the gas, mcs delta T. Now, I'm going to be moving into my phase changes. So I've got my phase change, but I have to be careful. Phase changes, the delta H's for these are typically reported in kilojoules. Generally speaking, delta H will almost always be in kilojoules per either mole or gram. So my heat of fusion is in kilojoules, so I have to convert that over. I'm going to add all these up here, and I can't add kilojoules and joules without converting one to the other. Doesn't matter which way I go, I just have to make sure that I've got one converted into the other. And I'm going to do the same thing for the boiling. But I also have to watch out for another trap. My heat of vaporization is in kilojoules per mole. So not only do I need to switch over the kilojoules, I've also got to adapt for the moles. So I'm going to go ahead and I'm going to have my mass. I'm going to have to switch that with my formula weight to get into moles. Now I can use my heat of vaporization, and I got to get that kilojoules into joules. Okay, this is just annoying. It's not hard, it's just annoying. Now, what I'm going to do is I'm literally just going to add this mess up. So I'm going to take all of these numbers that I've written down, and of course I've left a bunch of sig figs, way more than I need, and then I'm going to add them all up, and then I'm going to get to my proper sig figs. So I could report this as 83,000 joules, or I could report it as 83 kilojoules. Either one's a legitimate answer. Obviously, context, if a question is specifically asking for one or the other, then obviously it's asking for what it's asking for. If you're not going through the entire heating cooling curve, obviously parts of this would be missing. If you started out with water at, say, 27 degrees, well, that's gone, and that's not a 0, that would be a 27. And different substances would have different of these things. There's one more thing to call your attention to. That's not really about the math, but it is about the math. Look at the size of these numbers. The change in temperature here wasn't very much. We're only talking maybe about a sixth of the change in temperature here. Well, you know, so this is a lot bigger, but of course the change in temperature was more, and the specific heat was double. Okay, that makes sense. But look at these. The heat of vaporization, that guy's huge. My energy for vaporizing this thing is loaded compared to, hey, all of the warming parts. Phase changes generally take an insane amount of energy when we're doing them. This can have a couple of consequences. One, it does take forever to boil water because you've got to put a lot of energy into it. But also, when you have, say, a phase change going on, it can generate a lot of energy and transfer lots and lots of heat. This is why steam burns are so bad. It's not that you're interacting with a lot of water. Frankly, sticking your hand in water would be more quantity, but as the steam condenses, it's able to transfer an insane amount of heat into whatever it's condensing on. Once again, we're using kilojoules for a reason. So just keep that in mind when you are working with phase changes, that the energy of your phase changes are generally going to be huge. So with that said, have a wonderful day.